All right, so since it's been a little while since we have met, I thought I would go ahead and just restart this lecture from the beginning. So this lecture is basically about nonlinear functions and how we can deal with that using linear regression. So far, we've found that our model does a pretty good job if we've got data that looks something like this. So we've got some sort of a linear relationship. Okay, so we've got this line of best fit y hat that we've learned how to calculate. You've got this beta 0 as our intercept. So that does a pretty good job of showing that relationship, of estimating that relationship. But let's say that, maybe that relationship between y and x isn't so linear. Okay, so maybe it's exponential like that. Maybe it's some sort of concave function. Okay, and if we try to regress the line of best fit, try to find the line of best fit, it might end up looking something like that. Okay, we're kind of overestimating it there, and then we're kind of underestimating it here. As this is exponential function, as time goes by, we're going to get even worse off. Now, what about this one? So maybe it would look something like this. Okay, we've got problems here too. So we're underestimating here. Overestimating there, underestimating here, and here it's even worse. Our model says we've got this positive relationship between x and y, but here it's actually pretty strongly negative. Okay, so that's a pretty big mistake that we don't want to make. So how can we do this? What can we do? Well, we can turns out we can, within the bounds of linear regression, we can introduce some nonlinear elements, and it's still a linear regression. Okay, so the first way we're going to do that is going to be the subject of this particular video, and that is going to be log transformation. Okay, so why might we want to use some sort of log transformation? Well, let's say that we have this relationship that I drew in the second panel, where it's exponential. Okay, so the relationship between x and y is some sort of exponential function. So what might that function look like if we drew it out? Well, maybe it would look something like this. Okay, now if I log transformed that, this should be a y. If I log transform that, a natural log is the inverse function of e. Okay, so it makes that e go away. We've just got whatever was in the exponent for it, which is this beta 0 plus beta 1x. Okay, and maybe if I drew that new relationship, okay, so instead of y, I've got the natural log of y and x, and maybe now it looks a little bit more linear. Okay, and so obviously here our model is going to give us a much better prediction than it would if we tried to produce that same regression but without transforming the y. Okay, so the issue with doing this, the tough part about this, is that it's going to actually change how we interpret our variables. So here's a table that comes from our book, and this is just an interpretation table for different ways so that our model could incorporate logs. This first one is this level regression. That's the same one we've been doing. Okay, So this is just y equals, we usually say beta 0 plus beta 1x. It just says alpha plus beta x here. It's the same thing. So we've got just some coefficient at beta 0, which is in this case alpha, which is our intercept. We've got our coefficient on x, which is beta in this case, which is just our slope. So we would say 1 unit change in x leads to a beta unit change in y. Now, what that's, we've added on a few different things to that. We've added on that we might want to say on average at the end, okay, because we know this is our estimate is basically our expected value of beta. So we might want to say on average, this is what we expect. If we're using multiple linear regression, might be a good idea to add in ceteris paribus or all else equal. Okay, we're holding these other things constant, so assuming these other things aren't changing, this is the effect. Okay, so that would be the how we would interpret this leveled regression. That's the same thing we've been doing throughout the class. But this model we just did above, where we're logging the y, and then everything else looks as normal. This is going to change our interpretation here. So it's going to be 1 unit change in x leads to 100 times beta percent change in y, all else equal. Okay, on average. So that should be pretty straightforward. And by the way, this is not going to be something that I'm going to give you on the exam. I do want you to memorize this. We are going to be doing all of our exams because of this, because of the coronavirus. You will be at home, but I'm not going to make it easy for you and put this on the formula sheet. Okay, so I would like you to try to memorize this. The third one is going to be a linear log regression, and that's going to be exactly how it sounds. This first bit is linear, and then the x is what is logged in this particular case. And here we would say 1% change in x leads to a beta over 100 unit change in y. Now, you might have noticed that whichever unit is logged, whether it's the dependent variable or independent variable, our interpretation turns to percentages. Okay, it turns to percentages. So this particular case, the log is on the x. So we're talking about a 1% change in x. Okay, and that leads to a beta over 100 unit change in y. This last one, log-log regression. So we might also call this, elasticity regression. Okay, and the reason is our interpretation for this one, where both the y is logged and the x is logged, our interpretation is just like it was for elasticity back in Intro to Micro. Okay, so we've got 1% change in x leads to a beta percent change in y. Okay, so that's, in other words, that's saying given something is changing by a certain percent, how much is something else changing by that percent? So that's exactly what our interpretation is for elasticity. Okay, so that's pretty much it for logs. We are going to do a quick example from the text. Okay, so if you've got your Wooldred's text, this is an example from that. Okay, so for this example, we've got log salary and as a result of sales. So we're talking about how much you're getting paid as a result of how much you sell. Okay, and this is a log-log model. Okay, so we're dealing with log of sales and how that affects log of salary. Okay, if we regress this, then we find our coefficient is equal to 0.257. Okay, so we go to our table here and we see that 1% change in x leads to a beta percent change in y. Okay, So for this, we would say that a 1% change in sales is going to lead to a 0.257% change in salary. Okay, so notice that when we're talking about these interpretations, we're going back to the original variable, okay, salary and sales. We're not saying a percent change in log sales. We're saying a percent change in sales. Okay, so make sure you don't make that mistake. Okay? All right, so that's just a simple example from your text. So what we're going to do next is we're going to continue in the next video talking about this nonlinearity. And in this particular case, we're going to talk about polynomials. Okay, so see the second video in this series to talk about polynomials.